as I've alluded to in a previous video, the Bohr atom had some problems. It was a really great first start, and for a while everyone thought Bohr had really uncovered the secret of how the atom worked and what it was like. But it began to show its weaknesses as more and more information became uncovered. So first I'm going to talk about something that at first looked like it might have been a problem for the Bohr atom, and then it didn't. It actually sort of reinforced his idea. But then later on, there were some failures that he couldn't get around, and the model of the atom had to be adjusted pretty significantly, and we'll talk about how that happened later today. First, we're going to start out with a quizkin related to the things that we learned in the last video. So this asks us, what is the wavelength of the line that corresponds to a change in Bohr orbit of n equals 4 to n equals 1? Let's solve this problem. Stop the video, give it your best shot. I'll give you an answer and a solution in a minute. There are at least a couple ways to solve this problem. Most of you are probably going to do this, use the Rydberg equation to answer this question. So 1 over lambda is the Rydberg constant times 1 over the low number, which is 1 here, squared, minus 1 over the high orbit number, which is 4. So if we take 1 over 1, that's just 1, minus 1 over a 16th, so that leaves us with 15 sixteenths. So we could rewrite this, 1 over lambda is equal to the Rydberg constant times 15 sixteenths. Or we could say that lambda is equal to 1 over the Rydberg constant times 15 sixteenths. So let's evaluate this. 1 over the Rydberg constant is 109,678 per centimeters times 15 sixteenths. Well, here's what we come up with. Everything's exact here except the Rydberg constant, so we have a lot of sig figs. 9.72544 times 10 to the negative 6th, and remember this is in centimeters, so our wavelength is in centimeters. Let's calculate this in nanometers, because that's kind of what we seem to end up using a lot. So 9.72544 times 10 to the negative 6th centimeters. And here are some facts. I know 100 centimeters is the same thing as a meter. And I know that 1 meter is 10 to the 9th, or a billion nanometers. So when I do this, I find out 97.2544 nanometers is my wavelength. The next question is asking, what series is this line a part of? The visible series, Balmer, the Paschen series, which is infrared, or the Lyman series, which is ultraviolet. Well, remember, the visible light that we can see ranges from 400 nanometers up to 700 nanometers. And if it's longer than that, that's IR. And if it's shorter than that, that's going to be UV. The answer that we had was 97.3 approximately nanometers. Well, that's less than 400 nanometers, and so that means we're in the UV wavelength. So this was the Lyman series. Bohr's idea that the electron was a classical little particle orbiting around the nucleus didn't really work with some of the new things that were being uncovered at the time. One of them was, this guy here, Louis de Broglie, was starting to publicize the idea that matter, like light, exhibits a wave-particle duality. Well, Louis de Broglie was actually able to show that the wavelength of any matter wave is equal to Planck's constant divided by the mass of the particle times the velocity. V here is not nu, it's actually V, and it stands for velocity. So it's easy to see why large objects don't show a significant matter wave. So you can throw a baseball at me and I don't see a wave, I see a particle. It's because the mass of that baseball is quite large. And so in the denominator, a large number is going to make a very short wavelength. In fact, so small that it doesn't even appear to be a part of the matter itself. Now at first this seemed like it would be a problem for the Bohr model of the atom because the Bohr model was based on a classical particle. But it actually sort of supports Bohr's model because it explains something. It explains why in his second postulate he found that angular momentum had to be equal to n times h over 2 pi. Here's why. If you think about these two pictures of a standing wave in a circular orbit, the one on the left would be possible because for a wave to be a standing wave, it has to be continuous. there can't be any gaps or discontinuities in it. So if I tie a string to a doorknob and I vibrate the end of it up and down, I'll get a wave that'll stand on that string. But if somebody reaches in with his scissors and snips the string, my wave disappears. It can't exist anymore with a gap in it. Well, if we look at this model and think about this wave as sort of going around in an orbit, here's a wavelength, go through, down and up and back up again. There's another wavelength, down, back up. There's a third wavelength. Here's another wavelength. There's another wavelength, and it goes back to the top, and there's a node there. I can't just start and stop in any random spot because there's a discontinuity there. It has to be an equal number of wavelengths around the circumference. Well, think about this. The circumference is 2 times pi times the radius of the orbit. And that has to be a whole number of wavelengths. So n times lambda, where n is, here it is again, 1, 2, 3, and so forth. Kind of like this. You can have 4 wavelengths, that's okay. You can have 5 wavelengths, that's okay. But 4 1/3 wavelengths is not okay. So let's continue to work with that. As we've said, the circumference, which is 2 pi r, has to be equal to n times the wavelength, a whole number of wavelengths. So n here is 1, 2, 3, etc. Now, de Broglie is saying that lambda is equal to Planck's constant over m times v. So let's put the two together. 2 times pi times radius has to be equal to n times Planck's constant over m times v. I'm going to multiply both sides by m times v. So I have 2 pi r mv is equal to n times Planck's constant. Now I'm going to divide both sides by 2 pi. R mv is n times Planck's constant divided by 2 pi. But mvr, that's angular momentum. So angular momentum has to be n times h over 2 pi, which is exactly what Bohr, although he didn't know why, concluded had to be the case for his orbits. Well, there were still some problems. Bohr's atom failed for several reasons. One of them was every time they tried to apply this to atoms that had more than one electron, it didn't work. It would not correctly predict the line spectra of the atoms. They tried to use fancier math. They tried to modify it a little bit. They just couldn't make it work for multi-electron atoms. It just didn't work at all. And then this guy, Werner Heisenberg, showed that the velocity of a particle and its position cannot be known simultaneously. You can't know both of them at the same time without a certain amount of uncertainty or error. And when the particles were as small as electrons, that error would be so big that what Bohr was saying, here's the electron right in this orbit and it's going exactly this fast, it would be impossible to do that. Let's take a look at a little demonstration of that. This isn't exactly what Heisenberg was saying, but it gives the idea of the uncertainty principle and why it exists. So here's a boy that's blindfolded. He's in a room. He knows this ball is going 5 meters per second, but he doesn't know where it is. The only way he's going to be able to find out where it is by coming in contact with it. Now he knows the ball is right at his shin, but at the point he determines that, he actually interferes with the ball's motion and changes its velocity. That's what Heisenberg was saying. The only way we can find out where the object is by changing its velocity. So the next big advancement came with this guy here, Erwin Schrödinger. Erwin Schrödinger started out not from classical physics. He said we can't assume that an electron is going to act like a classical particle would. We have to take into account the fact that it's really a standing wave. So he's thinking about electrons as if they are standing waves. Schrödinger was particularly well suited for this because he was kind of an expert in standing wave mathematics. And he knew stuff like this. If you imagine a string, like a violin string or a piano wire or a guitar string, stretched between 2 points and locked there at those points. Let's say it has a length that's L. If you vibrate that string, there are several different ways it can set up a standing wave. There's one, there's another, a third, and a fourth. Now, all of these 4 ways of vibrating have something in common. Let's look at the wavelengths. For this mode of vibration, from the end to the other end is 1/2 of a wavelength. 1/2 of lambda is the length of the string, because this is half of a wavelength. It goes down and up, but it doesn't do that up and down again that would complete the wave. So if we solve this equation for lambda, we see that lambda would be 2Ls. Here's another one. This mode of vibration has exactly one wavelength between the ends. So lambda here is equal to L. Here's a wavelength and a half in L. Well, lambda then, or the wavelength, is 2/3 of the way. Each node is a third. 2 of the nodes makes up a wavelength, so wavelength is 2/3 L. Here's this other one. This mode of vibration, we have 2 waves. So lambda is actually 1/2 of L. And you couldn't have anything else and still have it be a standing wave. It has to be fixed at the ends. So you have to have a node at the beginning and L away from that. So there aren't any other modes of vibration unless you just have more nodes. So we could have like 5 halves of a wave. We could have that vibration. So you could keep going up to infinity. But you can't have anything like in between these different modes of vibration. So string waves are quantized. Let's look at how this could be described using an n number, a quantum number. I'm going to rewrite these things. Lambda is 2L, but I could say lambda is 2L over 1. Here's lambda is L, but I could rewrite that as lambda is 2L over 2. Lambda is 2/3 L, or lambda is 2L over 3. Do you see in the quantum number develop? Lambda is 1/2 L, but 1/2 L is 2L over 4. So here's our quantum equation. Lambda is equal to 2L divided by a number n, where n is 1, 2, 3, whole numbers only, and you could go up to infinity. There's no reason you couldn't. But you couldn't have 2.5 in there, and you couldn't have 3.5, or 1 2/3. Got to be positive whole numbers. So there's a quantum number, and it describes the wavelength. So Schrödinger develops this kind of mathematics of describing these electron waves. It's called quantum mechanics. Here are some of the ideas of quantum mechanics. One, the electron's a wave, but it has different forms of waves. Just like our string has different modes of vibration, the electron can have different modes of vibration as well. So each waveform of the electron is characterized by a certain energy level. When we see energy changes in the atom, it's not a particle electron jumping from orbit to orbit. What it really is the electron changing its waveform from a less energetic waveform to a more energetic waveform, and then coming back down again as it releases energy. Just like our one-dimensional guitar string wave required one quantum number, three-dimensional electron waves are going to require 3 quantum numbers. Here's what they are. N is the principal quantum number. L is called the secondary or the orbital quantum number, and M sub L is called the magnetic quantum number. These 3 quantum numbers go together to help describe the electron wave. Now, it's way more complicated than a simple string wave. In fact, each waveform's function, which is this Greek letter psi right here, as its abbreviation, is a solution to the Schrödinger equation. Now, here's the Schrödinger equation. You're going to look at this thing and think, why is he even showing this to me? I have no idea what it means. Well, you can have some idea what it means. This is actually just the law of conservation of energy. E here is total energy. This V function is potential energy, and all this other crazy looking stuff, that is kinetic energy. Now, we don't have to know what's going on here, but there is something I'd like you to note about this. Psi shows up in all the terms. Here's psi in the potential energy term, and here's psi in the total energy term. So what this is this is an equation that's called the differential equation. A differential equation is an equation whose solution isn't a number. Like in algebra in high school, you solve the equation and the answer is a number. Or if it's squared, it's two numbers. A differential equation, the solution to it isn't a number, but it's a function. It's a whole equation in itself. Well, each set of n, l, and m sub l, each set of quantum numbers, gives a different solution that's called an eigenfunction for that Schrodinger equation. Now, physicists continue to think about this as waves, and that's very correct. But for chemists, most often a particle interpretation of Schrodinger's theory has been developed. Here's how this works. Each psi is associated with a region in space that's called an orbital, in which the electron is likely to be found. So instead of saying, here's where the electron is, we just say, if you could find the electron, where are you most likely to find it inside the atom? Now here are the characteristics of these orbitals. They're centered on the nucleus. And it's all about likelihood. It's about probability. Where are you likely to find the electron, not where is it for sure going to be at any given time. Because you can't know that. Werner Heisenberg's uncertainty principle says you're never going to be able to do that. So here's how they're organized. The atom has different shells. Shells are divided into subshells. And subshells are clusters of orbitals. So the basic region where the electron is likely to be found is called an orbital. And we have several of these in many kinds of atoms. Orbitals are organized into subshells, and a few shells are organized, and a few subshells are organized into a shell. And there can be several shells in an atom. So this is the basic idea of the organization structure of the atom. Orbitals are where electrons are likely to be found. Orbitals are grouped into subshells. Subshells are grouped into shells, and there can be more than one shell in the atom. Now, how do these principal quantum numbers help us develop a particle view of the matter? Well, the principal quantum number has this range. Its range is 1, 2, 3, and so forth up to infinity. That's n. We've seen that quantum number's description before. This is sort of like the address of the electron in an atom. N designates what is the main energy level, or shell, that the electron is in. This would sort of be like your street for your address. The bigger n is, the farther away from the nucleus the electron is on average. We don't know where it is at any given time, but on average, if n is bigger, it's going to be farther away from the nucleus. The secondary quantum number, which is L, has a range as well. Its range is, starting at 0, it can go up by integers, 0, 1, 2, 3, up to 1 less than n. So the value of L depends on what shell it's in. L designates the individual subshell or sublevel that the electron is in. So if n is your street number, if you're an electron, L is like the house number on your apartment building. Because L and n both have positive integers as their designators, we often substitute letter designations to help avoid confusion. So S is a 0, L equals 0, we call that an S sublevel or subshell. If L is 1, we call it a P subshell. L is 2, we call it a D. L is 3, we call it an F. Those are the ones that are most common, and then it is possible to have L is 4 or 5, and the letters just keep going up, G and H, and if L was 6, it would be I. But S, P, D, and F are the ones that we're going to see most commonly. The magnetic quantum number, it has a range as well. The magnetic quantum number depends on the values of L. So it can range from negative L up to positive L, but only through integers. So for example, if L was 2, this would be the range of M sub L. Negative 2, negative 1, 0, positive 1, positive 2. Those would be the possible values of M sub L. Each value of M sub L represents an orbital. Every M sub L designates an individual orbital. So if I have 5 values of M sub L, that means I would have 5 orbitals. So let's kind of lay all these numbers out here. If n is 1, L can only be 0, because remember, n minus 1 is the maximum possible value of L. M sub L ranges from negative L up to plus L by integers. Well, if L is only 0, the only possible value of M sub L is 0. That means there's only one possible orbital when L is 0, and that subshell letter is S. If n is 2, you have two possible values of L. One of them is 0, which means M sub L could only be 0. That's an S subshell, and we've already seen that contains one orbital. But if n is 2, then L could be 0 or 1. So if L is 1, M sub L can now range from negative 1 up to positive 1. So that would be minus 1, 0, or plus 1. When L is 1, we call that a P subshell. And there are 3 values of M sub L, so that tells us that there are 3 possible orbitals in a P subshell. N is 3. L could be now 0 or 1 or 2. We've already seen for 0, which is an S sublevel, there's only one orbital. And for 1, M sub L can range from negative 1 to 0 to positive 1, so that's a P subshell, and it has 3 orbitals in it. But if L is 2, M sub L can range from negative 2 to negative 1 to 0 to plus 1 to plus 2. And that's 5 different values, so that means there are 5 different possible orbitals. The M sub L in your address is like your apartment number inside your apartment building. It designates more precisely where you live. If L is 2, we call it a D subshell. Now you're seeing a pattern develop here, counting up by odd numbers for SPD, and so F is probably going to be 7. Let's check it out. If n is 4, then you could have 0, 1, 2, or 3 for values of L. That means you can have an S, a P, a D, or an F sublevel. M sub L for L equals 0 could only be 0, so that's one orbital. And for P's, we saw minus 1, 0, and plus 1 translates to 3 orbitals. And for L is 2, which is a D sublevel, we've seen that minus 2, minus 1, 0, plus 1, and plus 2 translates to 5 orbitals. And so if L is 3, M sub L can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3, which is, of course, 7 possible M sub L values, each of which stands for a separate orbital. So there are 7. So if you look at the structure of an actual atom up to n equals 3, this is how that chart actually looks. The atom contains 3 shells. The n equals 1 shell, shell 1. The n is 2 shell, and the n equals 3 shell, which is shell 3. The first shell has got one subshell, that's the L equals 0 subshell, or the S subshell, and that has one orbital in it. When n is 2, you have 2 subshells. One of them is the L equals 0, or the S subshell, which has one orbital. But the second one is the L equals 1 subshell, which is a P subshell and has 3 orbitals in it. Each one has its own separate orbital designator, or M sub L. The third shell in this atom has 3 sublevels, or subshells. The S subshell, 1 orbital, the P subshell with its 3 orbitals, and the D subshell with its 5 orbitals. That's sort of the layout. Now, they don't actually look like these little boxes on this chart. What do they really have for shapes? Well, to get at the orbital shapes, we're going to take a look at some eigenfunctions, some of the solutions for Schrodinger's equation in a hydrogen atom. This is going to be, you're going to see some crazy, freaky looking, very complicated equations, and I don't want you to be turned off by them. I want you to look at what you can understand and not focus on the things about them that you can't understand. So to develop this, we need to have an axis system. Now here's X, Y, and Z axis, but we're going to think about these things in terms of polar spherical coordinates. So here's what that means. The nucleus is in the center of this axis, and that little round sphere there, I'm going to use that to designate where is the electron. Now one way that we can measure in spherical polar coordinates is how far are you from the nucleus. So that's R. That's one of our measurers. And then in the XY plane, how far are you from a designated starting point? we call that phi. That's the Greek letter phi. And then the third thing that you need to know is how far are you up? What's your angle up from the xy plane? And that measurement we're going to call theta. That's the Greek letter theta. So there's our axis system, r, theta, and phi. Now, if n is 1, L is 0, and m sub L is 0. So we're talking about the 1s subshell here. This is the eigenfunction. Psi 100 is 1 over pi times z over a naught raised to the 3 halves times e to the minus r over a naught. Now, what's constant and what's not constant here? 1, of course, is constant. So is pi. Z is 1 for hydrogen. It's just the charge in the nucleus. A naught is a constant number. You don't have to know what it is, but it's constant. 3 and 2, of course, are constant. E is a constant, and it's raised to a ratio of r and a constant. R is the only one of our 3 variables here that can actually change. So this depends only on the value of r. That means it's symmetrical in all axes. So going back to our axis system here, the likelihood of finding the electron only depends on how far away you are from the nucleus. So it's a sphere. You can go in any direction as long as you're r away, and the likelihood of finding the electron there is the same. Here's n equals 2, L equals 0, m sub L equals 0. So this is the 2s orbital. Here's the eigenfunction. Constant, 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 not constant, constant, not constant, constant. The only 2 things that can change are both the same thing. It's r. So this depends only on r. So for s sublevels, they're all symmetrical in all axes. So that means they're spherical. So the 1s, the 2s, and the 3s all look spherical. Now there are nodes in there. There are places where the probability of finding the electron diminishes, and we're going to see why that is later. But the basic idea is they're all spheres, and the bigger the n, the bigger the sphere. For n equals 2, L equals 1, and m sub L equals 0. So this is one of our 3 2p orbitals. Here's the eigenfunction. Psi 210 is constant, 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 not constant, constant, constants, not constant, and theta is not constant. So this depends not just on r. It depends on r and theta. So going back to this, here's what that means. As long as I specify how far I am up from the xy plane, and as long as I specify how far away I am from the nucleus, as I go around in phi, no matter what my angle is, the probability of finding an electron there is the same. So this is going to be symmetrical around the z-axis. And in fact, if you do the mechanics with the fancy math that they invented, this is what it looks like that orbital would look like. It's called the 2pz orbital, and it's like 2 nodes, 2 regions in one orbital that are centered on the nucleus, and they line up right on the z-axis. Here's another one. N is 2, L is 1, m sub L is plus 1. So this is another one of the 2p orbitals. Okay, let's look at what's constant and what's not. Constant, 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 not constant, 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 not constant, not constant, not constant. So now this depends on r and theta and phi, all 3. So we're not going to find any symmetry on any axis. It's going to matter where you are in terms of r, where you are in terms of the angle theta, and where you are in terms of the angle phi. This is the remaining 2p orbital. N is 2, L is 1, m sub L is negative 1. Constant, 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 not constant, 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 not constant, not constant, not constant. So once again, no symmetry. It's going to matter where you are in r, theta, and phi. So for these 2 remaining orbitals, this is the shape that you have. They're not on z-axis. It matters where you are in this plane. It matters what phi is. It matters where you are in this plane, so it matters what theta is, and it matters how far away you are. The probability of finding an electron gets bigger and then smaller again as you get farther away, so R matters. They are centered on the nucleus, and there are 3 of these things, a set of 3 orbitals in a p sublevel. Now this probability density comes from this idea. If you take psi, psi doesn't really mean anything. But psi star psi, which is sort of like psi squared for functions, does mean something. And it turns out to be proportional to the probability of finding an electron. So these are plots of R, of the R part of psi star psi for a bunch of different sublevels. This one is actually n equals 1, L equals 0. So this is the 1s sublevel. You can see that the probability is very low at the nucleus, gets high, and then it drops off. Where does it get high? Right, its highest point is actually right at Bohr's first orbit radius. So it's not an accident that Bohr happened to bump into that number. Here's n equals 2, L equals 0. So this is the 2s. It gets up and then down. There's our node. And then back up, and its highest probability is right at Bohr's second orbit. This is 2p. This is actually the 2pz. It starts out low, maximizes at Bohr's second orbit, and then drops off. So what we're graphing here is the probability of finding the electron at any position R. 3, 2 nodes. That's a 3s. Here's a 3p. 3p actually has a node. Here's a 3d. Doesn't have a node, but its probability on average for all the 3s happen to be at Bohr's third orbit. The d orbitals, there's 5 of them, and they're more complex, and the f orbitals are even more complex. We'll talk more about what to do with these things later on.